Hello and welcome to my YouTube channel. Today we will see the torsion. It's a very interesting topic in strength of material. What is torsion? Before that, I would like to explain a simple machine element that is known as a shaft. So what is shaft? Shaft is nothing but a machine element which is used to transmit the motion or torque. So shaft is used to transmit the motion or torque. That element, machine element, is nothing but it's a shaft. Now when this particular shaft is acting a twist or torque, if I apply the torque, so what is torque? Torque can be defined as force into perpendicular distance. So in this case, if you observe, when you apply a tangential force, so here if I consider tangential force, so that will be the tangential force into radius from this point to the center. So this is nothing but radius r. So if you multiply tangential force into radius, then we will get the torque. Now when, if I consider this is a circular shaft, the shaft may be a solid one or shaft may be a hollow one. When we apply a torque, when we apply a tangential force in this direction and on the upper side, and at the bottom side if we apply tangential force in this direction, then what will happen? It will become a couple and it will start twisting. Clear? So here if you observe this particular shaft, then if you apply a two tangential forces, that is pt in this direction and pt2, let's say this is tangential force 1 and tangential force 2, then if you observe the force is at distance of radius r, then what will happen? We will get the maximum torque. So here if you observe, here we can say maximum because r is the maximum radius of this particular shaft. Now when this twisting is takes place, due to that, when the two tangential forces are acting and movement is act on the shaft at the tangential direction, then it will go for the twisting, and that is nothing but a torsion. A shaft is said to be in torsion when equal and opposite torque are applied on the two ends of the shaft, then that is nothing but a torsion. So here if you apply a torsion on the both the shaft, clear? So when you apply equal and opposite, now if this torque is in this direction, if I consider this direction, then we must apply torque at the other end in this direction, so the direction will be this one. Clear? So when equal and opposite, so like this, so if this for torque is acting in this direction, then at other end the torque must be act in this direction. So when two equal torque but in opposite direction at the two end, when it is acted, then it is considered as a torque. Now we learn the basic thing. Now we will observe how the torque will vary. Now here I am considering a shaft. Now it is fixed at one end and one end of the shaft is free. Now here I will consider the section or plane AA and section or plane BB. So this is the front view, and if you observe this shaft from this direction, then I will get a circular view over here. So this is the front BB plane, and at the rear side there is a AA plane is there. Now this particular line I have drawn, that is the point CD. So if I measure this length CD, then I can consider this is the total length of this particular shaft, and it's having a diameter D. Simple. So this is a simple shaft is there. It is fixed at one end, and here we are going to apply a torque. Clear? Now, as you observe, when the torque is applied on this particular bar, now here when we consider torque applied, then we must apply a tangential stress. Clear? So at this in the direction in bottom, when we apply torque, then twisting may happen. So let's say this is figure A. Now here, after applying the torque, now here the end is fixed one, definitely it will apply the opposite torque what we applied over here. So same plane will be there, AA, this plane BB. Now this angle of twist, so if I consider the previous line CD, so this is one shaft, and here I have considered center line. At this center line I am considering the line that is known as a CD. Now what happened, this end is fixed one, and when we apply a torque, so when we apply a torque, then this particular D point, so earlier which was at point D, then it is get twisted. So here I will get another point is D point. Now angle of twist I will consider that is phi. Now when I observe same shaft from this direction, then I can say this is center point O, then this was the point D, then it is get twisted when we apply a torque. Clear? So when we apply a torque, then this point D is get shifted. So when we observe from this direction, then I can observe the angle is theta. Simple. So this is a simple case is there, a shaft is there fixed at one end, we applied the torque at this end, then the line which was earlier at the center line, it is not on center line, at the circumference, if we draw a line that is CD, when we apply a torque, then it is get shifted from D to D dash. So at this cross sectional area, so from this view you may observe the thing. So what is happening, so from this view if you observe, this is getting twisted because of the torque value. Clear? So before explaining the equation for the torque, I would like to explain the assumptions in the torsion. So first assumption is material of shaft is uniform. Whatever the material we have used, that it must be uniform throughout. Next, when we consider about the twist, so this is the twist is uniform along the shaft, so this twist must be uniform along the shaft. So twist must be uniform, material must be uniform. Clear? Now third assumption is a shaft is of uniform circular section throughout. So if you measure the diameter at different section, say at AA, at BB, if I draw another plane over here, then at every section the circular section must be uniform. Circular section must be uniform at different plane. So fourth assumption is cross sections of the shaft which are the plane before the twist must be remain plane after the twist. So here if you observe the cross sectional BB, this is the one plane, so after twist also it must be remain same. Clear? So cross sections of shaft which are plane before twist must be plane. Clear? So I will show you over here. So let's say this is a small shaft. I am considering one small shaft. So after twist, this should not be happen like this. Clear? So here if you observe the diameter at different location, it is different. The plane cross sectional area, it is something inclined. So previously it was 90 degree. So this should not be happen in case of torsion, and while we explaining the or while we deriving the equation. And last assumption is already which are straight before the twist must be remain straight after the twist. So if you measure the radius at different section, so if I consider this case, so here if I measure the radius, then here I am getting the same radius which was earlier. Clear? However, if you observe here, if I measure the radius, it is become reduced what I have observed previous. So this should not be happen while the twisting. Clear? It should be the shaft must go for the pure torsional. Clear? So these were the assumption we must understand. Now while derivation, if you observe, what should you uh, remember in exam? So you must remember these two angle, that is phi and that is theta. So when the shaft, so here I will show you the shaft. So let's say this is an shaft. Clear? So this is the center line of the shaft. Now at the circumference, so when you observe from this direction, then at this circumference, if I draw one line which is at equal height at center line, so this point is nothing but C point and this point is nothing but D point. Now what is happening when you apply a torque on this particular body, then this D point is getting shifted over here. Clear? So here if I join this, then this one is nothing but D dash. So this is a shaft. When we apply a torsion, this D point is getting shifted. So this D point is on circumference. You may observe over here. Clear? So this point is on circumference D to D dash. Clear? So I hope you understood the simple equation concept how the torque will go for the twist. Clear? Now let's see, when we apply a torque, then shear strain will induce inside the shaft. Clear? Now distortion, so here I will write distortion at outer surface due to torque T. So it is nothing but D dash. So this is nothing but distortion which is takes place at DD. Okay. So I will consider this one is figure A1 and figure 2. Clear? Now if I evaluate shear strain, so here we applied the tensile force, so we get the shear strain at outer surface, then it will be equal to the distortion at outer surface divided by length of shaft. Clear? So if there were the simple tensile test at the time, what was there? If you apply a force over here, then this was the length and after application of force there will be a change in length. So strain, simple strain was delta L divided by L. Now in this case we are applying a tangential force. That's why we get the shear strain at the outer surface. Clear? So that's why I am writing shear strain, that is again a distortion at the outer surface divided by change in length. So distortion I can write here d dash divided by L. Clear? Now from this I can get that if I want to evaluate the tan phi, what is the value of tan phi? If I consider this is an right angle triangle CDD dash, then can I write like this D dash divided by CD, and instead of CD I can write L. So if you compare these two, then here I can write tan phi. Simple. Now if you consider the mild steel, which is mostly used a shaft material, clear, or C45 shaft material, in that case if you observe, when you apply the force, then this phi angle it is very less. Clear? And the angle if angle phi is very small at the time, we can say that tan phi it will be a phi. Clear? So same equation I can rewrite, that is phi equal to dd dash divided by L. So this is one equation we get. So I will write as this is equation number 1. Now we have to write, or we can observe this triangle. Clear? So if you consider the arc d dash, and here theta is there, so if I want to evaluate from this figure, clear, so I am here writing from figure 2, I can write arc value of d dash, that will be equal to OD into theta, and OD is nothing but it's a R into theta. So I will show you here how this equation came. So this was the D, this was the D dash, and this was angle theta. Simple. And if I want to evaluate this arc, so this figure is nothing but this one. Clear? And if I want to evaluate this arc d dash, then I can write theta into OD. So if I consider this is O point, so then what is this? This is nothing but R. So I can rewrite R theta. Sorry, R theta. I am just putting this value of d dash in equation 1. So I can write from equation 1, phi will be R theta divided by L. So this will be the equation number 2. Now from equation 1 and 2, from equation 1 and 2, I can write 5. Okay, so we have already written over here R into theta divided by L. Clear? So this is the equation through which we can evaluate the angle of twist. Clear? So this is in the torsional. Now let's consider the property of material. Now I have already assumed that material of shaft is uniform throughout, so modulus of rigidity will also remain same. So I will evaluate modulus of rigidity, that is C, sometimes it is also denoted by Z. It will be the shear stress produced divided by shear strain produced. So this phi is nothing but is a shear strain and shear strain. So I will rewrite equation over here, tau divided by R theta divided by L. So it can be written as tau into L divided by R into theta. Clear? So if I rewrite this equation, so I will get, if I multiply theta over here, then I will get C into theta divided by L, that will be equal to tau divided by R. So this is our first equation we get. Clear? So I will call it as a equation number 3. Now given shaft is subjected to a given torque T, then value of the C, value of C, theta and L, these will be a constant. This is the material constant, so angle of twistivity will be remains constant, and length of shaft, it will remains constant. So in this equation, if I consider these all are constant, then I can rewrite this equation, that is tau divided by R, it will be equal to constant, or I can say tau is directly proportional to the R. Clear? So shear stress is directly proportional to the radius of shaft. Clear? Now from this I can say over here, it's a very important topic. Now if torque is directly proportional to the radius, so here if I want to draw a shear stress diagram, then at the center R value will be 0, so shear stress will be 0. So at the outer edge, so if you observe at the outer edge, then I can say that I will get the maximum shear stress at the R equal to maximum. So at the outer edge, so this is the center, at center R will be equal to 0, at the outer maximum radius will be there, so I will get the maximum stress. Clear? So from this equation you must remember, at center there will be 0 shear stress, at outer of the shaft, so at this outer edge of the shaft there will be a maximum shear stress. Clear? So if q is shear stress, if I consider q is a shear stress induced at a radius r from the center of the shaft, then tau divided by r equal to q divided by small r. Simple. So this is the another equation. Now this is the radius measured from center, and this is the shear stress induced in the shaft at radius of r. Clear? So if I consider this is equation number 4, then from equation number 3 and equation number 4 I can rewrite this equation, that is tau divided by r equal to c theta divided by L, that will be equal to q by r. Simple. So this is one equation which we have derived. Clear? So remember, shear stress at the center, it will remains 0, and it will be increased and it will be maximum at the outer edge of the shaft. Clear? So here if you consider the cross section area at center, shear stress will be 0. Clear? And it will be maximum at the outer edge. I hope you understood the concept of torsion and how this equation is derived. Now we will move further and we will see the maximum torque transmitted by a circular solid shaft. Now shaft may be a hollow or shaft may be a solid. Clear? So we must consider these two cases. So first I will consider a solid shaft, then how much maximum torque it can be transmitted, that we can evaluate it over here. So for that purpose I will draw a diagram. Wait. So here I will consider a solid shaft. Now for this, on this particular solid shaft I will consider a center point. So let's say this is center point. Now here I will consider one ring. Assume this as a circular one. Okay, let's say this is a circular ring. So this is a cross-sectional view. Clear? So same shaft will be there. This view I am drawing. Okay, I am not drawing this one, I am drawing this one. Clear? Now here if you observe this cross-sectional from this side, then I am considering a small strip at a distance of r. So if I measure this distance, this is distance r. Clear? And if you measure the radius of particular this shaft, so this is capital R. Clear? So how can we evaluate the area of string? Let's calculate the area of a ring. Now I will consider that is dA. It will be, so at the inner side if you measure the area, that will be 2 pi r perimeter, 2 pi r. And if I multiply the thickness, now here I am considering thickness will be a dr. Clear? And if I multiply with the dr, then I will get the area of this particular ring. Clear? Now I will use the same equation which we have derived over earlier, that is tau by r equal to q by r. Okay, so this is a shear stress at outer side. So here I have considered capital R, and it is equal to shear stress at radius of small r. Clear? Now if I simplify it, then I can write, I am taking this r in this side, so tau divided by r into small r. Simple. So this is equation. Now we will consider the turning force. Clear? Turning force on the elementary circular ring. On this particular ring I will evaluate the force. Now how we can get the force? That will be a shear stress acting on the ring into area of ring. I am using a simple formula, that is stress equal to force divided by area. Now here I am using shear stress, so I will get the shear force. So just multiply by this shear stress with the area. Now as I am evaluating for this particular ring, then I must consider shear force acting on this ring multiplied by area of the ring. So shear stress acting on the ring is tau into tau by r into r. So from this equation. Clear? So if I consider this is equation number 5, so from equation number 5 I can write shear stress tau divided by r into small r into area of ring, that is 2 pi r into dr. Simple. So this r, then it will become r square. So tau by r into 2 pi into r square into dr. So what is this? This is the force, turning force acting on the small elementary ring. Clear? Now I will evaluate turning moment on the elementary circular ring. Clear? So what is the formula for moment? Moment is nothing but force into radius. So I am using same formula over here. Clear? So that is dt equal to this turning force into radius or distance. So tau by r into 2 pi into r square into dr multiplied by radius. So if I multiply r over here, then r square into r cube. So I will get turning moment tau divided by r into 2 pi into r cube divided by r. Now what I want total turning moment or maximum torque acting on entire body. So for that purpose, what I will do, I will take the integration. So here I can write total turning moment clear. I'm evaluating total turning moment. So here I will consider the integration from 0 to r. Clear? So this is 0 to maximum outer up to r. Clear? So this will be the dt. Clear? If I consider this equation 7, then I can write from 0 to r tau divided by r into 2 pi into r cube into dr. Now tau divided by r and 2 pi, it's constant. So I will rewrite over here 2 pi into 0 to r cube into dr. So what is the integration of r cube? That is r raised to 4 divided by 4. So tau divided by r into 2 pi into, I will put limit r raised to 4 divided by 4, 0 to r. Simple. So this 2 get cancelled over here. Then I can rewrite again tau divided by r into pi by 2 into, so if you put the value of r, then it will be r square r raised to 4, 0 raised to 4. So here I can rewrite tau divided by r into pi by 2 into r raised to 4. Clear? Now instead of r, I can rewrite in terms of diameter, that is r equal to d by 2. So if you put in this equation, then tau by r into pi by 2 into d by 2 raised to 4. Clear? So this will become tau by r into pi by 2 into d raised to 4 divided by how much? This will be 8. Then the total torque or maximum torque transmitted T, that will be equal to pi by 2 into 8, 16 into tau. So wait, this is 2 raised to 4. It is different. Here again we need to put r. Here instead of r, I will write d by 2. Clear? So 2 raised to 4, it is 16. It is not clear. Now here this 2 and 2, it will get cancelled. This 2, it will go in upper side, so there is 2 pi 2 tau divided by d into pi divided by 2 into d raised to 4 divided by 16. This 2 get cancelled, d and 1 d will get cancelled. So what is remaining? So pi by 16 into tau into d cube. Clear? So this is the equation from which we can evaluate the maximum torque transmitted by a circular shaft. Clear? I hope you understand the concept. Now again we can evaluate, because shaft may be a solid or shaft may be a hollow. So I will write torque transmitted by hollow circular shaft. So for that purpose I will consider hollow shaft over here. This is the inner side. So if you consider weight, okay, so let's say this is an hollow shaft. Clear? Having center over here, let's say this is an radius Ri. If I measure radius of outer, then this is nothing but it's a R. Clear? Now what we will do, we will consider again one elementary strip over here. Consider this is circular. Clear? Weight consider this is also a circular. Clear? And radius of the circular elementary strip at a distance of r. Clear? Having some thickness. Clear? Okay, so this is the thickness. Clear? So let's say thickness is dr. Simple. Now same procedure we will follow. That is shear stress at the elementary ring. Clear? Shear stress at elementary string, that is q. So as we already derived over here. Clear? So that is tau by r equal to q by r. So from equation I will rewrite q, it will be equal to tau into r divided by r. Clear? So here I will write ro, and here also this is nothing but it's a maximum radius, outer side radius of the shaft. So at this hollow shaft there is an inner radius ri, and at outer side this is the radius of ro. So I must write ro. Next I will write turning force on ring. So that will be equal to Q, that is shear force acting on ring, into area of ring. Clear? So obviously area of link, again it will remain same. So tau into small r divided by capital Rho into 2 pi r perimeter into thickness dr. Clear? So that is the nothing but turning force on a ring. Simple. So I will rewrite this equation, that is 2 pi into tau divided by Rho into r square into dr. So this r into r square into dr. Now next is turning moment on the ring. Turning moment on the ring. So we must multiply with the radius r. So here I will write dt, that is equal to 2 pi into tau divided by Rho into r square into r into r. Simple. So I will rewrite r square into r cube. So that is 2 pi into tau divided by Rho into r cube into r. So this is the turning moment on the ring. What we want total torque on this particular entire object. So for that purpose I must consider the integration. So here I will write total turning moment, or we can say total torque on a body. Total torque on a body. So that will be T integration. So here can I write from 0 to Rho? No. Why? Because this is a hollow shaft. So in previous, if you observe, this is the entire solid shaft was there. So at that time I consider limiting from 0 to R, capital R. So here from Ri to Ro, that is internal shaft radius and outer shaft radius, inner shaft radius and outer shaft radius into dt. Clear? So I will rewrite this equation. Ro, sorry, it's a Ri from Ri to Ro. Clear? So here I will get 2 pi into tau divided by Rho into r cube into dr. So if I simplify it, then this is a 2 pi constant into tau divided by Rho is also constant. Then integration from Ri to R0 r cube divided by dr. So here I will get the integration tau divided by R0 into, in bracket, r raised to 4 divided by 4. So what is the limiting value? That is Ri Ro. Clear? So here I will get simplified form tau Ro into, so I will put the limit Ri raised to 4 divided by 4. So 2, it will get cancelled over here. So I can rewrite pi by 2 into tau divided by R0 into Ro raised to 4 minus Ri raised to 4. Now here I can rewrite R is equal to d by 2, Ro is equal to d divided by 2, or Ri equal to di divided by 2. Then I will get equation pi by 2 into tau into, instead of Ro I will write do divided by 2 raised to 4 minus di divided by 2 raised to 4. So instead of this Ro I will write dO divided by 2. Clear? So if you simplify this equation, then again I will get pi by 2 into tau, then dO raised to 4 divided by, so what we evaluated, 2 raised to 4, that is 16. 16 minus di divided by 16 raised to 4. Clear? So here I can write dO. So these two I will consider over here. So these two and these two, it will get cancelled. So I will get pi into tau into, so I will get consider 16 as a common, then dO raised to 4, sorry, di raised to 5, 4, sorry, divided by dO. So I can write dO over here. Clear? So if I write total torque acting on a hollow shaft, then pi by 16, I am taking 16 over here, into tau into dO raised to 4 minus di raised to 4 divided by dO. Simple. So this is the total torque you can evaluate on the hollow shaft. Clear? Now what is the purpose of shaft? It must transmit the motion or torque or power. Clear? So next topic of discussion in this topic is power transmitted by any shaft. Clear? So obviously you might have known this equation, that is power, it will be equal to 2 pi nt divided by 60. Clear? So unit of this power is in watt. Clear? So this is nothing but it's an rpm, revolution of shaft in rpm. Clear? And this t is, it's not a maximum torque. Clear? So this is a very important concept you must learn. This is not a maximum torque, this is nothing but it's a mean torque, or you can say average torque. Clear? So this equation can be right, power is equal to omega t. So this is angular speed, this is nothing but it's a 2 pi divided by 60. However, this is very important, please remember, this is the mean torque, and what is this? This is the maximum torque. Clear? So this is the mean torque in Newton meter. Always consider this unit, Newton meter. When you consider power in watt, this unit of this torque is in Newton meter. Clear? So this is a very important topic we must consider. Now next topic we are heading, so that is nothing but expression or torque in terms of polar moment of inertia. Clear? So in engineering mechanics you might have learned the polar moment of inertia. Polar moment of inertia of a plane area is defined as moment of inertia of area about an axis perpendicular to that plane. Clear? Now I will explain in simple way. If you consider this is an circular area. Clear? So if I consider this axis is x-axis. Clear? So here I will consider this is x-axis. So here I can write y-axis. Clear? What is polar moment of inertia? Which is perpendicular. So this is along z direction, and this polar moment of inertia izz can be given by ixx plus iyy. So this you might have learned in engineering mechanics. Now what we want, we want to evaluate the polar moment of inertia of a circular cross-sectional in perpendicular direction. So if I consider this image, any, you can consider any shaft, so along this direction to this particular plane, so this is the plane, and if you consider this is a plane, then along the perpendicular direction, that is nothing but polar moment of inertia. Clear? So that we must consider in along z direction. So how I can write? I can write the moment, we can say dt, that is a moment on a circular ring is given by equation which we already learned, that is dt, that will be equal to tau by r into 2 pi r cube into dr. So here I am not explaining new thing. So here if you observe while derivating the solid shaft, so this equation from equation 7, what is dt? That is tau by r into 2 pi into r cube divided by dr. Clear? So this is from equation number 7, that is moment on circular ring. Clear? So here I can rewrite this equation, tau divided by r into 2 pi r into dr into r square. Clear? Now here if I rewrite again, tau by r into 2 pi r into r square into dr. Clear? Now here if you observe the area, what we learn, that is area of that ring, that is 2 pi r into dr. Instead of 2 pi r into dr, can I write dA? Yes, because this equation we consider the area of that elementary strip. So this strip, or we can say this element strip, so 2 pi r into dr, so that will be the area. So if I rewrite this equation, then I can get tau by r into r square into dA. Clear? What is moment of inertia? That is moment of area. Second moment of area is nothing but moment of inertia. Clear? So here I can write total torque, that will be equal to T, and it is again integration from 0 to r. Here I am considering solid shaft, so that must be dt. So this is the equation of dt. So I can write from 0 to r, tau by r into r square into dA. Clear? Now here I will consider this is tau by r is constant, so I will take outside tau by r into r square into dA. So what is this? This is nothing but it's a moment of inertia of a circular object about an axis perpendicular to the plane of circle and passing through the center of circle. Clear? So this is the moment of inertia. Second moment of area is nothing but moment of inertia, or we also called as the polar moment of inertia. It is in perpendicular direction. So here I can write that is polar moment of inertia J equal to pi by 32 d raised to 4. How this come? Because I z equal to ix plus Iy. So moment of inertia, it is pi by 64 d raised to 4 plus pi by 64 d raised to 4. So if you consider any circular area in x-axis and along y-axis, if you evaluate, then it will be remain same. So from this I can get 2 pi by d raised to 4 divided by 64. 2, you will get pi by 32 d raised to 4. Simple. So again, from this equation, so let's say this is equation number 10. So from this equation, can I write T equal to tau by R into J, that is polar moment of inertia. So here I can write T by J, that is equal to tau by R. So let's say this is equation number 11. So tau by R we have already written over here, tau by R, clear. So let's say this is equation number A. From equation A and 11 I can rewrite, from equation 11 and A I can write T by J equal to C theta upon L, that is equal to tau by R, clear. So in this equation, this is nothing but it's a total torque or maximum torque which can transmit by solid or hollow shaft. This J is nothing but it's a polar moment of inertia along the perpendicular direction to the plane. So this C, here we can write G also, that is modulus of rigidity. So this is an theta angle of twist, sorry, that is the angle. This total length of shaft. This is shear stress acting on a shaft when radius is capital R. This is R is nothing but it's a radius of shaft, clear. I hope you understood this equation. This is the very important result we got. From this one equation we can solve any kind of numerical based on the torsion, clear. So next a small concept is there, that is polar moment. Polar moment, it is a ratio of polar moment of inertia, which we already learned, to the radius of shaft, clear. So it is denoted by ZP, polar moment, that is J divided by R, clear. So this is a small concept, polar moment, simple, that is a polar moment of inertia divided by radius of shaft. So if I evaluate for solid shaft, then ZP will be equal to, so what is J? J is nothing but pi by 32 d raised to 4 divided by R. So instead of R I will write d by 2, that is 32 into d raised to 4 divided by d by 2. So here I will get ZP equal to pi by 16. This 2, it will equate pi by 16 into d raised to cube. So this equation will give the polar moment of solid shaft. Next one, if you consider for a hollow shaft, then what will be the changes? So obviously J will be equal to pi by 32 do raised to 4 minus di raised to 4. So ZP will be equal to J divided by R, clear. So here I will write RO, then pi by 32 do raised to 4 minus di raised to 4. Just instead of RO I will write do divided by 2. So here ZP, that is polar moment for the hollow shaft, it will come pi by 16. So the 16 do into do raised to 4 d raised to 4, clear. So in simplified form I will write pi by 16 into do raised to 4 minus di raised to 4 divided by capital Do. Simple. So in exam they may ask you about the polar moment. Clear? Now the last topic of discussion for the today's lecture, that is the strength of shaft. Clear? Strength of shaft and torsional rigidity. Now strength of shaft means maximum torque or maximum power of shaft can transmit, that is known as strength of shaft. Now what is torsional rigidity? Torsional rigidity is nothing but it's a product of modulus of rigidity into polar moment of inertia of the shaft. So from the small formula you can evaluate the torsional rigidity, that is multiplication of the modulus of rigidity, that is G or C, into polar moment of inertia. So this torsional rigidity is also defined as the torque required to transmit or produce a twist in one radiation per unit length of the shaft. So what is the signification of this rigidity? It is nothing but it's a amount of torque. So amount of torque is required to twist by 1 radian per unit length of the shaft. So this is all about the torsion of the shaft. I hope you understand the concept torsion, torque transmitted from the shaft of solid shaft, hollow shaft, the main torsional equation, then polar moment of inertia, polar moment, and torsional rigidity. If you like the video, then you can subscribe the channel. Thank you.